start.
Hi, we are Team 1014, and we will be doing SCUDEM Problem A about binging contaminated chocolates. I am Essam Ackleh from Killian Hill Christian School,
I'm Edward Huang from Oconee County High School.
I'm Anshul Gokul from Forsyth High School.
and our advisor is Professor Gregory Mayer from the Georgia Institute of Technology. Heavy metals are known to have significant health problems if they continue to accumulate in the human body. We were given an article on the potential heavy metals found in contaminated chocolates. We are trying to construct a mathematical model that will analyze the long-term dynamics associated with these heavy metal levels in children who consume chocolates that are contaminated with them. We're going to analyze different levels of consumption, especially on holidays such as Halloween and Christmas. We're also going to look at the effect of birthdays being located near or far away from these holidays. And we're going to look at how these heavy metals diffuse throughout the body over time.
So we're going to approach the model using a three-compartment model. There we have an input, which is how the heavy metal is introduced into the bloodstream via chocolate consumption. There it is diffused at various rates among the different parts of the body, which represent the different compartments. And we have an output, which is how the heavy metals are eliminated through the metabolic and excretory process in humans. However, over time, some of these organs are going to accumulate these metals, and this is what we're trying to observe. So the first one we have is lead. So lead is introduced into the blood via chocolate consumption. There it is diffused at different rates, which are these variables A21, A31, into different compartments, such as tissues, bones. Lead can also leave the human body through urine, which is from compartment 1, or through nails, sweat, and hair, which is from compartment 2. So we have these functions that can represent the compartments. So d of x sub 1 of t dt represents the rate of change of lead in the compartment 1, which is the blood. So there, lead can diffuse into other parts of the body. It can also be introduced into the blood from different parts of the body, such as the tissues and the bones. L represents the amount of lead that is introduced into the body via chocolate consumption for the day. Similarly, we have d of x sub 2 of t over dt, which represents the rate of change in lead in compartment 2, which is the tissues. There, lead can be introduced into the tissues from the blood, or it could leave the tissues where the lead diffuses back into the blood, or it leaves into the external environments. And lastly, we have the d of x of 3 sub t over dt, which represents the rate of change of lead in the bones. There, lead can enter the bones from the blood, or it could leave the bones and diffuse back into the blood. So we can reorganize these functions into the function on the right, which is x prime is equal to a of x plus b, where x prime represents the rate of change in these compartments, and a represents the functions we obtained from earlier, and b represents the amount of lead that is introduced via chocolate consumption for the day. So here are the lead diffusion constants, and plugging these constants into our matrix, we obtain the matrix down below. And for B, 0.3 represents the median amount of lead introduced into the body via chocolate consumption for the day.
Now we looked at the steady state final values that would result from this median intake of 0.3 micrograms per day. We used a model that we previously developed using these coefficients, and we looked at the steady state and we plugged it in a model using pretty much Euler's method and seeing the end state that we would get.
So here we have the cadmium compartment model, which is very similar to the lead compartment model. So here cadmium is introduced into the blood via chocolate consumption. There it can diffuse into compartment 2, which is tissue, or compartment 3, which is kidneys. Cadmium can also leave the human body via fecal excrement from compartment 1, or through urine from compartment 3, which is the kidneys. And so here we have another matrix modeling our functions in the top left corner, and we have the cadmium diffusion constants in the bottom left corner. Plugging in those constants, we get the matrix in the top right corner, and in the bottom right corner, we have B is equal to 2.73. So the 2.73 represents the median amount of cadmium introduced into the human body via chocolate consumptions for the day.
We could essentially do the same thing once again. We take our daily intake of 2.73 and plug it into our model that we previously developed right here. And we're going to find our still steady state values to find our median level of cadmium that should occur in the body.
And so lastly, we have the arsenic compartment model, which is very similar to the other two we have previously. So the arsenic is introduced through chocolate consumption into compartment one, which is blood. There, it can diffuse into other compartments such as skin, kidneys, hair, and the liver. Arsenic can also leave the body via urine into the external environment through the blood. And so here we have arsenic modeling. So in the top left corner, you have the matrix associated with the functions. And in the bottom left corner, you see the arsenic diffusion constants. And plugging in those constants into our function or our matrix, we obtain the matrix in the top right corner. And then for B in the bottom right corner, we have 0.75. 0.75 represents the median amount of arsenic introduced into the body via chocolate consumption in a day. We are measuring in micrograms.
We finally do the exact same thing once again. We take our 0.75 uptake of 0.75 micrograms per day, and we find the final steady state values that would occur in the blood, the body tissue, as well as the liver, and we find our total steady state mass as well. So now we look at the sort of application we get from the steady state. So we start off our initial baseline values as the stored steady state values that should naturally occur from this normal daily uptake. But now we also include a binge. Now these binges occur, New Year's, Halloween, Christmas, and Easter. And we can see that these binges result in these massive spikes of consumption of these heavy metals due to chocolate having these large doses of heavy metals, right? So plus 400 micrograms results in the spike above a healthy level. And our sort of healthy level is around 66 micrograms in the total body. And this results in, we sort of shaded in the area that is an unhealthy level. And as we can see, this area, we can see whenever we have the spike for roughly, a few months after, we still are in these unhealthy areas as our body tries to get rid of the heavy metal through the ways to get into the external environment. And we can see we have these various spikes, and we can see it also enters our tissue, but to a lesser extent, and it also leaves. So in order to keep track of that, we kept the track of days above this total healthy level, and we kept it as a percentage. So right now, when we binge on these holidays, only on these days, and we have a celebration close to Christmas, this year it would be New Year's, we have a result in 45.1% of days being above this healthy level. Now we look at a birthday separate from other holidays, right? So we have this Easter, we essentially took out this New Year celebration, replaced it with the birthday separate from Christmas. And now we have 51.8% of days above this healthy, which is actually more than we had before. Before we had 45.1%. But a major difference is our spikes are not as great, right? We see the spike at roughly 200, well, up to 300 really due to the continued effect of Halloween from Christmas. But now, if we looked at the previous one, we had up to 400 here, and essentially what happens is our spikes are much greater, and our spikes are much less high, but they are more spread out due to another date being here, the birthday in this case. Finally, we look at when we have a distributed day of binging throughout the day. So instead of having a sort of concentrated day of just eating all that intake, we spread it out over the next 30 days of the holiday. And in Easter will be our first case we distribute that over a month. And we can see our peaks are less rare, right? In our previous case, our Easter peak were roughly above even 400, but now our Easter peak is up to around 250. And as we see, the peaks are much shorter. But in addition to that, they're much wider, right? That would naturally happen due to the longer days of binging. And we keep track of the percentages above, and we get 60.1% days above this healthy limit of 66 micrograms in the body. And then we looked at one final case where we had no intake except those one-day binges, and we result in sort of less decay than any of our previous cases. We see that, of course, we have our spikes post holidays, and it slowly decreases, in fact, at a much quicker rate than the other cases, and that results in the least amount of days above this dangerous threshold, which would definitely make sense as we want to minimize that heavy metal intake. And finally, our last case is we have no intake of heavy metals at all, except on those specific holidays, and we spread it out over 30 days. This results in a good deal amount, but our spikes are significantly decreased compared to all other times where we try to minimize that heavy metal intake.
In conclusion, we discovered that binge consumption results in a more accentuated spike in the heavy metal levels, but that's also accompanied by a faster elimination rate when compared to steady heavy metal levels in the body. Children with birthdays close to holidays experience heightened spike in heavy metal levels, while if they're spaced further from holidays, they result in sustained but more steady effects of candy consumption. Now, we could have improved our model by making our simplified compartment model a little more complex, as we could have considered different compounds in the blood, as well as different diffusion rates of these compounds, as well as within other organs. We could also introduce heavy metals from other variables such as air, water, and food. These are our sources. Thank you for watching.